In this example, a statistical process control monitoring system samples the inside diameters of 4 bearings each hour, and following table provides the data for k is equal to 25 hourly samples, means that there are 25 samples and each sample has 4 measurements. So we are asked to construct an x bar chart for monitoring the process mean. Okay, first of all, this is the data that you can see. uh, each sample, and the leftmost column is the sample number. You can see there are 25 samples and each sample has 4 measurements. So first of all, we need to calculate sample mean for each sample. So we can use this formula of average, and then copy it until the bottom. Like this, we have average of all samples, that is the sample mean. Now we have to calculate the average of sample means, this x bar. So we will use same formula, average, and but this will be the average of all sample means, like this. Okay, we got this sample mean value. This will be actually the center line for the control chart. Now we have to determine standard deviation for the samples, but for S we have to find out this standard deviation for all samples, all measurements in all samples. If there are 25 samples and 4 measurements for each sample, it means that this is the standard deviation for 100 measurements. Now we need to calculate UCL and LCL using the equations right next to these cells. We need to use the values of the average of mean samples and standard deviation. So it will be m6 plus 3 times m5 divided by square root of sample size, which is 4. And similarly, LCL will be m6 minus 3 times m5 divided by square root of the sample size, which is 4. Now we have all these values which are required to plot a control chart or x bar chart for monitoring the process mean. But in order to plot it in Excel, we need to copy this data means along each sample, so that we can plot it against all samples. We just need to copy it in these cells by fixing the row number. If we fix the row number by copying it until the end of the data, the row will not change and will have the same value all through the column. We'll do the same for UCL value. Just copy it and fix the row, and then copy it until the end of the data. And we'll do same thing with LCL. Just copy it, copy the cell value, fix its row, and then copy it until end of the data. Okay, now we have arranged our data so that now it's in the form that we can use the plot function for plotting our control chart. Highlight all of these 4 columns and then use the recommended chart, and you'll get this. This graph has 4 plots on it. The blue line which has random variations is the actual plot of sample means. The top horizontal gray line is UCL. The red line in the middle is the center line, and the yellow line at the bottom is LCL. So by plotting this, we can see that all of our data of the sample means, which is indicated by this random the blue line with random variations, is well within these two lines, means well within UCL and LCL. So it means that our process is in control. If some data is falling outside these upper and lower control limits, it means that there is some problem in the process of the production that we need to address. As long as it stays within these limits, we are fine. Okay, in the next example, a manufacturer of ballpoint pens randomly samples 400 pens a day and tests each to see whether the ink flow is acceptable. The proportions of pens judged defective each day over a 40 days period are listed in the table below. Construct a control chart for the proportion P defective samples in of n is equal to 400 pens in the selected process. So you can see that this is a list of 40 days of data, and the second column represents the proportion of defective pens found each day. Okay, now our next step is simply to calculate the average of the defective proportions. We'll use the formula over all of these. For 40 samples, proportions of defective pens in 40 samples. Then we need to calculate UCL using the formula written just next to the UCL cell. It is the average of P plus 3 times square root of average of P times 1 minus average of P or proportion divided by n sample size, which is 400, because 400 samples are tested, and out of those, like for example in the first day, only 0.02 proportion of those 400 samples is defective. Now let us calculate LCL using the formula written under this cell. So it is average of the proportion minus 3 times square root of average of the proportion times 1 minus average of proportion divided by sample size, which is 400. Okay, I think there is some problem in the formula. Yes, we need to there instead of minus there should have been multiply. Okay, just replace it with steric and press enter. We get this value. Now we have the average value of sample proportion, and we have upper control limit and lower control limit. We can plot it easily, but in order to plot in Excel, we need to copy all these values along each sample so that we have the same x-axis, and we can plot all those values along the y-axis. We'll do similar thing as we did before. Just copy the values of P average P, UCL and LCL within this column by fixing the rows so that the row number does not change as we are copying the data. Now our table is ready to be plotted as a control chart. We will highlight all these 4 columns and then plot them like this. Okay, so it is the same thing. The blue lines actually represent the data plot of the defective proportion in each sample. The top one is UCL and the bottom horizontal line, which is yellow in color, is LCL, and the red horizontal line in the middle is average of the sample proportion, and in this case this proportion is the proportion of defective samples. And that is all. If you have any questions or you do not understand something, you can ask me during our live interactive session. Thank you very much.